Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Okay, so Alhamdulillah pada petang ini kita berkesempatan untuk mengadakan program fizik workshop bersama dengan Dr. Afiq daripada Talis University. So without further ado, kita akan mulakan majlis kita. Okay, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Yang berbahagia, Ketua Projek bagi fizik workshop iaitu TS Dr. Suziana binti Omar. Kita ada bakal doktor. Okay. Yang dihormati penceramah jemputan kita iaitu Dr. Afiq Arif bin Aminuddin Jafri. Okay. Maaf saya, Dr. Afiq Arif bin Aminuddin Jafri. Yang dihormati rakan-rakan pensyarah serta pelajar-pelajar sekalian. Bagi memberkati majlis kita pada petang ini, saya ingin menjemput wakil pelajar kita untuk sesi bacaan doa iaitu Ahmad Muizzuddin bin Ruslan.
Bagi memberkati lagi majlis kita mulakan dengan umul kitab Al-Fatihah. Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala asyrafil anbiya wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma innaka khalaqal azim, innaka sami'ul alim, innaka ghafurur rahim, innaka rabbul arsyil azim, innaka barrul jawarul karim. Ya Allah, Engkaulah yang mempunyai segala kepujian, Engkaulah yang berhak menerima segala kepujian, Engkaulah yang berhak menerima segala kesyukuran, Engkaulah yang memiliki segala pemerintahan. Di tangan Engkau segala kebajikan, kepada Engkaulah kami kembali segala keurusan. Allahumma ya Karim, ya Rahim, cucurilah rahmat dan rahim ke atas majlis fizik workshop yang diadakan pada hari ini. Berkatilah ia dari awal hingga akhirnya. Ya fa'ilu lima yurid. Kami juga memohon perlindungan daripadamu dari segala perkara yang boleh mencacat celakan majlis kami dan daripada segala perkara yang melalaikan kami dan berbuat taat kepadamu. Kepadamu juga kami serah segala urusan kami. Rabbana alaika tawakkal wa alaika anabna wa alaikal masir. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi wa sallam. Walhamdulillahi rabbil alamin.
Amin, amin ya rabbal alamin. So, terima kasih kepada saudara Ahmad Muizzuddin bin Ruslan kerana sudi untuk mengetahui bacaan doa. Okay, seterusnya saya ingin menjemput Ketua Projek bagi fizik workshop ini iaitu TS Suziana binti Omar untuk memberikan sepatah dua kata.
Okay, Assalamualaikum semua. Saya Suziana binti Omar selaku penasihat program pada hari ini. So, tahniah kepada semua yang hadir, kepada pelajar dan juga pensyarah. So, walaupun pada hari Minggu, so tahniah diucapkan kerana dapat menghadirkan diri untuk majlis ini. So, saya ingin memperkenalkan AJK yang terlibat untuk program ini. So, saya TS Suziana binti Omar dari FKE, Nik Nur Syahadah binti Nik Zulkifli daripada FKE, Rina binti Abdullah PKE, Muhammad Azri bin Abdul Razak PKE, dan juga TS Dr. Norizan Ahmad PKE dan Rosmawati Syafi'i PKE. Dan juga ini adalah pensyarah yang terlibat untuk menjayakan program pada hari ini berserta pelajar. So, ini pelajar yang menjayakan projek pada hari ini. Muhammad Azril Hanafi binti Azman, Ahmad Muizzuddin bin Ruslan, Afif Farhan bin Rosdi, Hamdi Rahman bin Roslan, Muhammad Syafiq Aiman bin Sulaiman, Raja Muhammad Amirul bin Raja Mamat. So, tahniah kepada semua AJK yang terlibat untuk menjayakan program pada hari ini. So, sedikit sebanyak saya ingin menjelaskan berkaitan program pada hari ini. So Fizik Workshop adalah salah satu inisiatif daripada UiTM untuk pengajaran kolaboratif. So pengajaran kolaboratif ini sebagai dikenali juga sebagai team teaching. So ia adalah satu pendekatan yang melibatkan beberapa tenaga pengajar dalam kalangan pensyarah dan juga rakan industri untuk bersama-sama beriringan untuk memudah cara pengajaran, mendidik, membimbing dan melatih pelajar bagi memperkasa pembelajaran kendiri pelajar. So untuk pengajaran kolaboratif, so kita pilih satu chapter iaitu chapter 5. So untuk PHY 145 juga terdapat di chapter 5 Work, Energy and Power, dan juga PHY 130 untuk Mechanical juga dalam chapter 5. So untuk chapter 5 ini dia akan membantu persediaan pelajar untuk PHY 130 untuk pelajar menghadapi ujian 2 dan PHY 145 untuk PKE untuk menghadapi peperiksaan akhir. So ini adalah pelajar-pelajar senarai kelas yang hadir untuk hari ini untuk PKE dan juga PKM. So itu sahaja daripada saya sedikit sebanyak berkenaan program pada hari ini. So diharap program ini dapat memberi manfaat kepada semua yang terlibat dan semoga majlis hari ini diberkati oleh Allah. So tahniah dan terima kasih.
Okey, terima kasih kepada Ketua Projek TS Suziana binti Omar. Okey, jadi sebelum kita bersama dengan kita punya penceramah jemputan ataupun pensyarah jemputan, saya ingin membacakan sedikitlah background ataupun latar belakang beliau. Okey, so pensyarah jemputan kita hari ini ialah daripada Taylor's University. Okey, diberi nama Dr. Afiq Arif bin Aminuddin Jafri. Beliau bertugas di Taylor's University di School of Pre-University Studies. Okay. Dan latar belakang akademik beliau telah memperoleh Bachelor of Science, which is dalam Applied Science daripada University Sains Islam Malaysia, dan beliau memperoleh Master of Science dalam Applied Physics daripada University Malaya Malaysia, dan beliau juga telah memperoleh PhD daripada Universiti Teknologi Malaysia. Dan kepakaran beliau adalah dalam bidang Optics Non-Linear and Quantum Optics. Kemudian Fiber Laser, Q-Switching Mode Locking, Ultrafast Laser, dan Optical Materials, Steerable Absorber. Okay, jadi without further ado, so I would like to call upon kita punya penceramah jemputan Dr. Afiq Arif bagi memulakan sesi penceramah beliau lah. Okay, so silakan Doktor.
Okay, thank you very much to the chairperson. Before I want to start, I would like to ask, my audio is clear to all of you?
Clear.
Ya, Doktor.
Clear, eh? Okay,
Clear.
good. All right. Okay, let me share my screen first. I haven't used my Teams for a while now, so give me a few minutes. I usually use Zoom. Okay. Is it showing my slide?
Yes.
Doktor.
All right. Okay, good. Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, especially to the head of program for this particular workshop today, TS Dr. Suziana, my lab mates actually at UM, and to all the lecturers and the students here. Okay, so for today's session, I would like to give a few sharing about work, energy, power. So as told by the chairperson, this is my academic qualification. Okay, I don't need to retell. Okay, These are a few things about myself. Let me use pointer. Okay, so I've done my industrial training at Existex Sdn Bhd in February to June 2016. This is my industrial experience. This is one of the semiconductor machine manufacturing company. So we do back-end test there. Okay. And then from 2012 to June 2016, I graduated with Bachelor of Science in Applied Physics from University of Science Islam Malaysia, USIM Nilai. And then September 2016 to February 2018, I graduated with Master of Science in Applied Physics with distinction from University of Malaya. This one, my area of expertise is also photonics. My research is in fiber laser. I started my PhD journey in May 2018 to September 2020. I have 2.5 years of research experience. This one is I started to be a graduate research assistant for 2.5 years. And concurrently, I also do my PhD at UTM. So I just graduated recently in March 2022. So from January 2021 till now, I am a lecturer teaching foundation student at School of Pre-University Studies, Taylor College. I've been teaching quite a few subjects now actually, Physics 1, Physics 2, Mathematics, and Engine Design Innovation. Okay, so I think I can start with my workshop. Usually when I do the workshop, I would like the student to also give me the feedback. So that means if I ask the question, so the student might want to answer the question. Okay, so we start off with the energy. In between the workshop, I will also show you guys one online simulation that I usually use during my teaching and learning. Okay, so let's just talk about what actually is energy. Energy is a measure of particles' capacity to do work. So anything that has particle inside our body, ourselves, has energy because it did have capacity to do work. And then energy is measured in joules or kilojoules, represented by joule or kJ or kJ. Okay. Energy exists in many forms. Right. This is just the introduction about energy. Okay. This includes electrical energy, chemical energy, heat energy, and light energy. And the two things that we will learn more today is mechanical energy. So mechanical energy, we usually talk about two important things. The first one is kinetic energy, and the second is gravitational potential energy. If we have spring, we will have a different energy. Okay. So here today, I will just talk about one-dimensional, two-dimensional motion without any spring involved. It's energy that a particle has due to either its motion or its position or both. Okay. Mechanical energy is the energy that will be considered in two forms. Okay, these are the two important forms of mechanical energy, which is the first one is kinetic and potential energy. So if something is moving, we call it has kinetic energy. If something has height, so it has potential energy. Usually we call it this gravitational potential energy. Okay, so what actually is kinetic energy? Kinetic energy is the energy a particle possesses due to its motion. So if something is moving, we have kinetic energy. They possess kinetic energy. Kinetic energy is defined as half mv square. Okay, this is the formula for kinetic energy, where m is the mass in kg. Okay, this is the things that I emphasize to my student. Let's just confirm that this your mass when you are doing the calculation is in kilogram, and then your speed is in meter per second, right? If you have it in another unit, so you need to change it or convert it. And then we have gravitational potential energy. GPE is the energy of a particle possessed due to its position. So if something is has position, and let's say I have this ball on top of a building, so it has a position, so I can it is stored energy. Okay, and then change in gravitational potential energy is defined as mgh. M for mass, g is acceleration due to gravity. Okay, this g, usually a few textbooks they will use 9.81 meter per second meter per second square. Sometimes you also use 10 meter per second. Okay, so physicists, they are lazy, they want to make things easy, so we just assume that it is 10. And then h is the vertical distance. Vertical distance, remember we have horizontal, which is this one is vertical, y axis, vertical distance. This one is horizontal distance x. Okay, so the student usually miss this. So this one is horizontal distance, this one is vertical distance. So something that has this vertical distance, it has gravitational potential energy. Why is that? Because if something has a height, right, so they will be influenced by gravity. Okay. Okay, this one I want the student to try. Okay, find the kinetic energy of the following: a particle of mass 0.5 kg traveling at 8 meters per second. Anyone have any idea? Can answer me? Maybe you can put your answer in chat box. I'm not sure how to make it. Let me end first. Did I still showing my screen? Did I still showing my screen?
Yes, we can see your slide.
Okay, slide. If the student want to answer, maybe you answer using you can turn on the mic lah. I'm not sure if you can answer by this. Okay. Okay, so anyways, I just proceed lah. Sorry, I'm not very familiar with Teams, but I'll just get used to it. To get rid of that one. Okay. Okay, so anyone who want to answer? No, it's okay. Okay, so what we have here just now is half mv square. So we use that particular formula to get the value of kinetic energy of this particle, where we have half, mass is 0.5 kg. Okay, remember this is the one that I told we need to convert it into kg. So this one mass is in kg, and then we have 8 meters per second. Okay, so we just substitute everything, we will get 16, which is in joule. Okay. So the unit here is in joule. So kinetic energy in joule, because you already converted all the unit in the appropriate unit. Okay, so a car of mass 900 kg traveling at 15 meters per second. Anyone have any idea who want to answer me? Student, I want student, not lecturer. Can turn on the mic if you want. Okay, so no takers. Okay, so we still use the same kind of formula, half mv square, right? So V is 900 kg, M is 900 kg, and V is 15. So we just substitute all the value, we get 101,250 joule. Okay, this is the kinetic energy. And last one here. This is the one that is a bit tricky, because usually the student forgot to convert this gram into its appropriate unit. Okay. So we have half mv square again, but converting 20 gram to kilogram, I have 0.02. So I put that into my equation. So I get the answer here to be 2,500 joule. Okay. So that is how we do the calculation for kinetic energy. Now let's move on to gravitational potential energy. Stating whether it is a gain or loss in gravitational potential energy. Okay, so we have some sort of new term here, gain or loss in gravitational potential energy. Never mind, let's just try to do the calculation first, and then you will see why is it a few we call gain, why is it a few we call loss. Okay, again, for GPE, so I have the formula is mgh, right? So we use this particular formula. Okay, mass is 2 kg, all right? Value for gravity is 9.81, and then vertical distance is just height. Okay, so we substitute all of it into this, so we get this to be my final answer. This is a gain in gravitational potential energy. A particle is raised. Okay, raised means that the particle is going up. Okay, so if something is going up, right, so I shouldn't put it in this form, it will not be accurate. If something going up like this and vertical distance, so it is a gain in gravitational potential energy, because sort of get more and more kinetic gravitational potential energy when it move, let's say, on top of this building. Okay, this is why we call it again in gravitational potential energy. Later on, I will show you the simulation so that you guys can see more clearly. And then we have the second one, 500 kg descending. Okay, descending going down. So that means the gravitational potential energy will keeps getting lower and lower. Okay, lower and lower. So it is decreasing lah. So decreasing means that I just do the calculation. It doesn't matter. M is 500, G is 9.8, and then H is 50. So I do the calculation. But this is lost in GPE. Why is that? Because it is going down. And then the gravitational potential energy keeps getting lower and lower. Okay. And then we have the last one here, climbing a vertical distance. So climb. So it goes up lah. Okay, going up, climbing. So it is still gain in gravitational potential energy because 80 times mgh times 9.8 and times 75, we get this. Okay, so this is how we sort of know we are dealing with any kind of energy. Okay, so these are one of the questions. Find the gain in kinetic energy of a car of mass 800. So I have 800 kg here. So this is the mass of this particular car. Accelerate from 10 meter per second. This is the velocity. Initial velocity. I can say this is VI. Okay. This is V final. Sometimes people call this initial to be U. Okay. It's up to how your lecturer teach you. So VI is initial. Okay. VF final is final. Find the gain in kinetic energy. Okay. So how do we do it? First, we just do the calculation. We know that kinetic energy, right? So let's say this is initial, half mv square. So mass, I should plug in the value of 800. And then V here, I should plug in 10. So 10 square times m times half. So I get this to be my final answer, which is 40,000 joule. Okay. So this is the initial kinetic energy where I take into account the initial velocity. So I can also do the calculation for final kinetic energy by looking at this. Okay. So the final kinetic energy, I put 25 instead of 10 just now. So I have this to be my final answer in joule. So if I want to know what is the gain in kinetic energy of a car, what do? I just do kinetic energy final minus kinetic energy initial. Okay, so this is a delta KE. Delta means that it is a change in kinetic energy. So final is 250, 250,000 minus 40,000. And then I've got 210,000 joule, which is the gain in kinetic energy. Okay. Okay, so we do one more before I show you the online simulation. Usually I use Kahoot to enlighten the class, but because Kahoot now they want premium, so I didn't buy it. Okay. So a child of mass 30 kg. So this is the mass of this child. Slides down a slide of length 4 meter. So we have a slide with 4 meter length inclined at an angle of 30 degree. Okay. So if you guys did learn free body diagram, you guys should know that we have some sort of this inclined plane problem, and then we have that 30 degree. Okay. So but in this question, it didn't involve any kind of this, so you don't need to worry. But we just need to use a bit of geometry so that you guys know how to do the calculation. Okay. So by modeling the child as a particle and the slide as a smooth inclined plane. Okay. This smooth particular word here is very, very important. Smooth inclined plane means that there is no external energy whatsoever, okay, that is acted upon this child. Okay, smooth means that there is no friction. No friction. Okay, so there is no friction. Okay, there is no friction on this inclined plane. So we can just neglect friction, find the loss of gravitational potential energy of the child. So we want to find GPE. I know that GPE, okay, GPE is the formula is mgh, right? Okay, mgh. But we don't have any kind of indicator of height. Okay, what we have here is 4 meter. Okay, let me just draw you guys this. Okay, this 4 meter is the length. here, this line, but the one that we want to find is this H height, okay, this height. Okay, so we need to find this height, right? So height is not given to us. What we have is mass, right? Gravity, we know that mg, g stands for gravity 9.81 meter per second, okay? But here we need to use a bit of trigonometry. How do we do that? Okay, from trigonometry, we know that, okay, so if we have an angle here, we can also find the side here, all right, if we already have the side here, okay? So I can use that trigonometry to just find H. So MGH, I can use 4 sine 30. Okay. Why is it sine? Sine because sine, so sine opposite over hypotenuse. I have opposite of this over hypotenuse. Okay, hypotenuse is this because this is 90 degrees. So hypotenuse is this 4 meter here. So what I can do here is opposite is H, okay, and then I have 4 meter over 4. So that means if I want to find H, I can do 4 sine theta, theta, so 30 degree. So that's why I have 4 sine 30 here. So MGH is this, so I can do the calculation. So I get 588. Again, the unit is in joule, okay. So therefore, this is a loss in GPE. Why is it loss? Because it is going down. Okay, something that is going down, it will influence, it will experience the loss of gravitational potential energy and the gain of kinetic energy, okay? So the things that I told you just now, I want to just emphasize it here, okay? Now let's try to, I add the slide first. Okay, I want to show you one thing that is very, very crucial. This one is one of the online simulation that you guys can use, okay? You guys can see to sort of give you the clue on how to do the physics related to work energy power. Actually, this is the open source online simulation from University of Colorado. I usually use this in my classes. So to get the student to understand and to experience how physics work. Okay, so this is one of the simulation from Colorado FET. The website is fet.colorado.edu.my. This is sorry, not .my. This is from University of Colorado. So you can see here the way I if we have someone one student, let's say Emma is on a skateboard, and then Emma want to try to move from this side to this side. Okay, so we can try to analyze what kinetic energy and gravitational potential energy that Emma experienced at each of the following point at the plane here of the skateboard. Okay, so I can try track skateboard track. The first thing that I can do, I can put energy bar chart here. I can put plus sign. Okay, maybe I give this to the chat box first. Wait, I share in the chat. Okay. So the student, you guys can try this, okay? Right, when I try this, the student can also try this so that we can, you guys can see it clearly, okay? So this is how what happened. Let's say Emma is at this position at the right end of this skateboard track, okay? So you can see what happened to the potential energy and kinetic energy. At this position, okay, Emma has the highest potential energy. You can see this potential energy, okay, but no kinetic energy. Why is that? Because Emma is just started to skating, right? So and then if I try to start moving, you can see what happened is this total energy, this is the total mechanical energy, needs to be equal to the addition of kinetic energy and potential energy, okay? So from that, you can see that energy, this is the principle of conservation of energy. Energy is conserved, okay? So kinetic and potential, when we add up, we get this total here. Okay, this is what happened. And the moment when we say, okay, I want to know where the kinetic energy is the highest. Someone is, sorry now, okay. Okay, so where is the kinetic energy is the highest? I can try to move it here. Okay, so I move it here. I can put it here. I try to redo it first. Okay, so you can see I can try to move, okay, at a few position like this, okay. There is no, we need to start at on the, okay. This is the moment where we have the highest potential energy because all of the energy is converted into potential. Some of it may be in kinetic because it is EMA is just started moving. But when I am at the bottom here, you can see what happened. Okay, so all the kinetic energy is converted. All the energy is converted into only kinetic energy. There is no potential energy left. So this is the moment where I say this is the moment of maximum kinetic energy without any potential energy. All right. Why is that? Because if we try to put a reference height here, okay, remember, I told you, if you something to have potential energy, it need to have height. Okay, if I put the reference height here at this position, that means EMA has height 0. So MGH is 0, so we don't have any height. You can also try to make the pie chart to be appear here. Okay, so this is what happened to EMA when it happened, and then you can see the speed of EMA. Okay, so this is where it got interesting when you can see that, okay, so at this point where the potential energy is the highest, okay, kinetic energy is none to, maybe we have a bit, and then maybe it is neglected because all of the energy is converted into potential. So you can see that the speed is very, very low, okay, in comparison to when it is here, right? So because it comes from half mv squared, okay? So you can also try to play around with the mass, or if you change the mass, what will happen? So this can give you the idea on what to do. You can also try to change the track, okay? So we can see what actually happened, right? So, yep. Can try to play around more with this slide, this website. Okay, I move on to the next steps. I just want to make sure that I am showing the screen. Okay, I'm showing it. Okay, now let's move on to work. Work can be defined as force time distance. So the work done by a constant force, let me change to laser pointer. By constant force is the force in Newton. So force needs to be in Newton multiplied by the distance moved in meter in the direction of the force. Okay. So something that has force and distance, we have work lah. If the direction of the force is different to the direction of motion, then we need to use this. Okay. So this one I usually try to break up the components so that the student can see why, right? First, I can try to do something like this. Okay, we know exactly that the direction of motion, D here is the distance from here to here. Okay, this is the distance D. Okay, one thing that you notice, if D is like this, but F is not sort of parallel to D. It is not parallel to D. So that gives us the problem. So whenever we want to do the calculation for work done, if it is without any sort of angle here, there is no inclination of this force, it's fine. But now you have the inclination of this force, so you need to change it accordingly. Okay. So why is it we have cos theta here? Because you can see that from force and free body diagram, if we have this force F, force is a vector quantity, we can break it down into X and Y. So we have Fy here. Okay. So Fx. So we can see that what happened is this Fx is the one that is parallel to D. So whenever we want to do the calculation for any work done, we need the direction to be equal. So instead of taking only F, we take F cos theta. Okay, we take F cos theta because from this angle, I can also put that. Okay, this one, if this one is theta. Okay, cos, right, cos is cos theta. Adjacent over hypotenuse. So adjacent over hypotenuse. So adjacent is this. right? Adjacent is the angle, the side right next to the angle theta. So this one is adjacent, so fx. Hypotenuse is f. Okay, so if I were to find the value for fx, I can do f cos theta. So that is where this f cos theta come from, like fd cos theta. Okay, so that you need to also make sure that the alignment of f forces and the direction of d is in the same direction. Okay. Now we move on to work question number 2. We have a particle of certain mass. Mass is given 2 kg, is pulled 3 meter along a smooth horizontal surface. Okay, again, horizontal is x. Okay, so smooth means that there is no external force due to the gravity. Sorry, no force due to the friction, not gravity. Sorry. Okay, no friction. Okay, there is no friction. That is why we put smooth here by a force of 8 Newton acting at an angle of 60 degree to the horizontal. 60 degree to the horizontal, this is like what we have just now. Okay, something like this. Again, we know that, okay, this distance here is the distance of 3 meter. Okay, so distance of 3 meter. If we want to do the calculation, we need to be able to make this force 8 Newton to be in the same direction as this D. So the only way we can do it is by looking at Fx. So again, we know that Fx is just F cos theta. So 8 cos 80. Okay. So from this, we can multiply it with 3, we can get the work done. Okay. So 8 times 3 times cos, 60. Not 80, 60. I erase this. Okay, so we've got the work done to be 12 lah. Okay, so that is how we calculate the work done if we have some sort of angle like this. Okay. Now we move on to work energy and dissipative forces. Still have quite a few time already. Okay, let's just establish the relationship between work and energy. This is the one that we call work energy principle. It allows us to sort of do the calculation easily when it comes to involving the work and energy. Okay, so when we have work done, we know that work done is equal to change in kinetic energy. Okay, this is the sort of established facts that we know. Then we can use that. This can be seen from the following application of Newton's second law. So our intention is we want to try to get this equation lah, work done equal to change in kinetic energy. Usually change in kinetic energy, we have delta KE. Okay, delta KE. Okay, so from this we can know Newton's second law. Okay, this time I want to ask student, what is Newton's second law? Anyone? You guys can turn on your mic if you want. What is Newton's second law? Newton's first law is inertia, third law is action-reaction law. What is Newton's second law? Any takers?
F equal to MA.
Okay, good. F equal to MA. I don't know if student or lecturer is answering, but it's fine. Okay, Newton's second law is F equal to MA. From this, a particle of mass m, kg is moved a distance of d meter horizontally by a constant horizontal force F. Let the initial speed be u. Okay, so we want to do the calculation based on F equal to MA, right? So Newton's second law, and then we want to know, okay, from the particular condition, and we have a particle of certain mass m, move distance d horizontally. Horizontal means that it is along x direction by a constant horizontal force F. Okay, constant horizontal force. Horizontal force means that, okay, D and F is in the same direction. So we don't need to worry about the trigonometry that we do just now where it involves sine and cosine, but this one we can just use F time FD. Then the initial speed U and final speed B, V. Okay. So by Newton's second law, F equal to MA, we can isolate A. We get A as the subject, F over M, right? So since the force is assumed constant, okay, so force is constant, the acceleration can also be assumed constant. Okay, why is that? Because from F equal to MA, right? Okay, so if A is constant, F is also going to be constant. Okay, so this equation here is one of the kinematic equation. Some books they call it Shubart equation. Okay, so from this Shubart equation we can try to sort of substitute this A equal to F over M into this. Okay, so I substitute where S is just the distance, U is initial velocity, V is final velocity. Okay, so we do the calculation here where I substitute this A, right? A here into this. So I get F over M times D. Okay, this S I substitute with D because from the initial condition, it is supposed to be D. Okay, and then I have V square equal to U square plus 2FD over M. So this is the calculation that the equation that we have established. And finally, I can try to multiply everything. Okay, I put the calculation here. Multiply everything with half M. Okay, that's why half at 2 at this will be gone, and then M at the last term here also gone. So I have FD and then half MU square, half MD square. So it turns out that this is the equation that relates between the change in kinetic energy. Okay, you guys remember change in kinetic energy delta KE, which is half mv square. V is final velocity, U is initial velocity, and then this one is work done. Okay, so W is equal to delta KE. So we can sort of establish this condition or expression so that we can do the calculation easily when we do the work energy principle calculation. Anyone have any question so far from the student?
No, sir.
Okay, good. Okay, now let's move on to the next part where we have this is one of the question. A particle of mass 3 kg. Okay, we have the mass is pulled 6 meter by a horizontal force. Okay, 10 Newton. Again, we have horizontal force across a smooth. Okay, again, smooth horizontal surface here give us the indication that there is no friction. Okay, no friction. Okay. Because there is no friction, if the particle started from rest, find its speed when it has traveled 6 meter. Okay, we will want to try to use the formula that we already derived before. Okay, so work done is equal to FD. Okay, again, because the distance and the force is in the same direction, right? So we don't need to do any trigonometry. So we know that work done is FD, so 10 times 6, so 60. Okay, so and then I have half mv square minus half mu square. So V, right? So we can see V is final velocity. Final velocity is 6 meter. 6 meter is the distance. Find its speed. Okay, so we want to find V. This is the one that we want to find. U is 0 because it started from rest. So this one I can put it go to 0. So now I can just equate these two. So I did know this one is 60, right? So I can do this calculation. So to do the calculation, I can come out with this. Since this one is also 0. So half mv square, M is 3, right? And then 60 is FD. So I am able to find the value for the speed, which is 6.32. The unit is meter per second. Okay, meter per second. So the speed of the particle when it is travel 6 meter is 6.32 meter per second. Okay. Move on to question number 3. Find the horizontal force that causes a particle of mass 2.5 kg to increase speed. Okay. So we have the mass of the particle here. I put here, this is the mass. Okay. And then to increase speed from 2 meter per second. So this is the initial speed. I can put U here. And then this 5 meter per second is V, final velocity, okay, over a distance of 10 meter on again smooth horizontal surface. Okay, smooth means that there is no friction. Okay, so since there is no friction, you don't need to take into consideration that one. Okay, now I have this kind of things here. This one is D. So I can do the calculation. I want to find horizontal force. Okay, the things that I want to find is F here. Okay, so again, I can use the same exact equation that I used just now, right? So work done equal to change in kinetic energy. So where change in kinetic energy, I can find the initial kinetic energy first, which is half mv square, sorry, mu square. Okay, so I have 5 meter per second. And then final kinetic energy is half still m, and then I have 5 meter per second here to be the final speed, 31.25. So change in kinetic energy is final minus initial. So final 31.25 minus 5, I get 26.25. So at the end, I can equate this change in kinetic energy with FD so that I am able to find my F, where D is already 10 meter. Okay, so I get the required force to be 2.625 Newton. Okay. And this is the last part before we do a few questions. A dissipative force is a force which causes a particle to lose energy. So dissipative force. So sometimes I call this dissipative force as the frictional force. So there is a few dissipative force that we have. So we can try to imagine when there is a particle, okay, rolling on something like this. So the particle rolls from here to here. So if this surface is smooth, it doesn't matter. What happens is the particle will have kinetic energy. Okay. So, but what happens is if this surface is not smooth, so I say the surface has friction. Okay, we cannot do the same kind of exact situation here, and we can tell that, okay, some of the energy, instead of it is in the form of kinetic energy only, it also loses in the form of dissipative force, or the one that we call friction. Okay, friction and air resistance are example of dissipative forces. The other things that we usually do is we also try to do some sort of calculation for air resistance. This one is related to the movement in y direction, okay, vertical direction. Usually we can do this for the parachute calculation. Okay, so we have work done against a dissipative force is equal to the loss of the total mechanical energy of the system. So work done against a dissipative force. So that means we have equal to the loss of the total mechanical energy of the system. So we know one thing, that mechanical energy, we have two, which is kinetic energy. This is, we try to not include the one related to spring first, kinetic energy and gravitational potential energy. So work done against the dissipative force will give this kinetic energy and gravitational potential energy the loss of energy. So they sort of will experience the loss of energy from this dissipative force. Okay, so this is the equation for this dissipative force. Actually, it is the same as the one that we have just now. W is equal to Fd, but instead of W being minus, when we do the calculation, now W being negative. All right, because it indicates that the energy is lost. Sorry, the work energy is lost. Energy in joule, work done in joule. Okay, so now let's try to do the provided calculation. A particle of mass 3 kg is moving down. Okay, so we have a particle with this certain mass of 3 kg. Okay, now we have a rough slope. Okay, rough slope, inclined at an angle of 30 degrees to the horizontal. The particle passes point A, so I can see point A here at 3 meters per second, and B 2 meters down the slope. Calculate the work done against friction. So for this calculation, we want to do the calculation to do to try to find W. W work done, but work done against friction, not the actual work done that we have before this. Okay, so for that one, pointer back. Okay, so the first thing that we need to do is we want to find the work done against friction. We can try to find the kinetic energy first. Why is that? Because from the kinetic energy, you guys recall from the previous slide, we have W is equal to delta KE. Okay, so if we want to find the here work done against friction W, we can try to find delta KE first. Okay, this is the mass lah, because from work energy theorem that we have just now, work energy principle. So gain in kinetic energy means that, okay, so when the particle is at this point A, so it starts to roll down, okay, it will experience the gain in kinetic energy. Okay, so half mv square, v square here is 4, okay, minus half mu square, 3 meter per second. Right, so this is to calculate the gain in kinetic energy. I have 10.5 joule. All right, so this is the amount of kinetic energy that the particle experiences when it rolls down the slope. Okay, now instead of calculating only that kinetic energy, we also need to do the calculation of height, right? So again, we have that the same exact calculation just now from when we do the calculation for the previous one, where we are given with this length of 2 meters. So when we want to find the height here, we can use trigonometry, because sine, okay, I put sine 30, sine 30 is equal to opposite, so opposite edge over hypotenuse. Okay, so if I know 2 sine 30, okay, I can know my value for h. Okay, so where I get my h to be 1. Okay, now instead of just knowing the gain in kinetic energy, because the particle is rolling down, and then we also have the loss in gravitational potential energy. Because at this position, I started here, try to this. So at this particular position A, okay, the particle started to have a very, very big gravitational potential energy because it has height, but the potential energy will start to lose when it goes further down to the point B. Okay, so when it touches point B, there is no more potential energy. So this is why we call it the loss in gravitational potential energy. So we do the calculation 3 times 9.81 times 1, which is the height that we have just now. And then we are able to get the value for the loss of energy, where I can have 29.4 joule, and then minus with this gain in kinetic energy. So I've got 18.9. Okay, 18.9 is the loss in energy. Right, so from the work energy principle, I can know that work done against friction is 18.9 joule. Okay, because at the start, the particle will has almost all the particle will has 29.4 joule kinetic energy. Gravitational potential energy, and when it starts to roll down, the gravitational potential energy will start to lose, and because at the bottom here, the energy left is only 10.5. 10.5 joule. So we can do the calculation where 24, right, 29.4 just now, minus 10.5, okay, this one, times this one, minus with this one, I get this. So this is how much friction take out of the system. So friction needs this 18.9 to sort of allow the particle to roll down the slope. Okay, any question from this slide? Because I think this slide is a little bit messy, and I hope you guys understand. Any question, guys, can ask? Already 1 hour. Okay, no question. Okay, now we move on to principle of conservation of energy. The total mechanical energy of a particle remains constant, which implies that no external forces acting on the object. Okay, so this one I told you before that if there is no friction, no air resistance, so we tell that the mechanical energy is conserved. That means all the energy will be the same inside the system. Okay, inside an isolated system, it will be the same. There is no loss of energy. Okay, the total mechanical energy of a particle is the sum of any kinetic energy and any potential energy. Right. So hence for a particle on which the only force acting is gravity, so we have initial kinetic energy plus initial potential energy equal to final kinetic energy plus final potential energy. So from this particular equation, we sort of know that initially, all right, so if we try to look at the slope situation just now, initially, all the energy is in this initial potential energy state. There is no kinetic energy whatsoever. Why is that? Because it is not moving. It is only staying at this position, okay, at this initial potential energy. So, and then all of them will be converted into kinetic energy because at this position, there is no height already, right? There is no height. So there is no final potential energy. So I can say that the energy is conserved lah. Alright, the energy is conserved. There is no loss of energy due to the friction. Therefore, loss in kinetic energy equal to gain in potential energy, and vice versa, gain in kinetic energy equal to loss in potential energy. Because if you gain kinetic energy, you will sort of lost kinetic energy. Potential energy. Let me just stop this slide first. We try to look back at the simulation to provide you guys more better understanding lah. Okay. Let me. Okay, so again, you can see here, this is thermal. Thermal means that this is the dissipative force, the force due to the friction, force due to air resistance. So we try to not put thermal first. Okay, we try to make this without any thermal energy. So you can see at the beginning, if I try to start this, all the energy is in the form of potential energy, okay, at this position, right? So if you see this bar here, there is no green, okay, green indicates kinetic energy, okay? So we call it is the loss of potential gravitational potential energy. Why? At this position, potential gravitational potential energy become lower. So that's why we call it loss in gravitational potential energy. So as soon as gravitational potential energy lost, kinetic energy will be gained, provided by this bar that you can see, bar pie chart that you can see. The green become more, and then the blue become less at this position. And if you try to look, you add kinetic and potential together, you can see the total here. Okay, the total will be more, right? So, and then I can try to look more, and then you can see. So, if I were to ask that, okay, at this particular condition, at this particular position, we have gain in potential energy because potential energy become more and more, but kinetic energy become less and less. Okay, so what interesting about this simulation is you can also try to put timer if you want. Okay, sorry, this one is not timer. Just now. Oh, okay, you can try to add friction. Okay, so let me try to add friction so you can see later. Instead of only kinetic and potential, you can see that there is some sort of thermal energy here. Okay, the green bar here starts to raise up, right? So that indicates instead of the energy divided into kinetic and potential only, it will also be divided to thermal. Thermal here is in the form of friction, is in the form of air resistance, but here we sort of provide more friction. Okay. Okay, and then you can see that there is the loss of kinetic mechanical energy. That is why this is the one that we call non-conservation energy. Energy did not conserve. It didn't only comprise of kinetic and potential, but you also has thermal. Okay, so a very interesting one. You can also try to do the measurement. If I were to do the same kind of situation, so I can measure at the exact situation. At this particular point, you can see that, okay, so at this particular point, we have 2390 joule, and then we have for potential energy, okay, kinetic energy is small, and then at this particular minimum, all right, minimum condition, okay, I'm having a hard time to make it appear. Okay, so at this particular minimum condition, you can see potential energy become 3.3. Why is that? Because you can see that the height becomes 0.01. So the height is sort of, you can say, negligible lah. So the potential energy become less. But the total, you add up kinetic and potential, you will still have the total mechanical energy. But when you start to add friction, you can see what happened. I try to stop it here, and we can try to measure. Okay, so this trap sort of try to take a few energy from this kind of situation here. Okay, why is that? Because it needs that energy because it has friction. That's why the energy didn't only be divided into 2, now it is divided into 3. So thermal will also change accordingly. I put it here, then the same thing happen. Okay. I go back to the slide. Okay, we are done with this. Okay, so if we are given with the same exact question, but now instead of telling that, all right, we have a smooth inclined plane, given that the particle start, this one we done. Find the distance traveled, write down a smooth inclined plane to the given that the particle. Okay, provided that this time mechanical energy is conserved, smooth surface, no work done against friction, so we can do the calculation now. Okay, so we want to calculate the find the distance traveled. Okay, for this question we want to try to find the distance traveled along the slope. So this is the one that we want to find. Let's say I put this as D. Okay, so we want to try to find this D. So how do we do the calculation? Provided that since it is smooth, so mechanical energy is conserved, so we don't need to worry about any friction due to this inclined plane or the surface of the slope. Okay, so what we can do here first is we can try, since it starts at rest, so the kinetic energy is equal to 0. Okay, but we know exactly at this particular position, this is the position where it has the maximum gravitational potential energy. Okay, I can say that GPE max. Okay, maximum gravitational potential energy at this kind of position. So I can see that, okay, I can do the calculation for that. If I want to find the distance, I can do the calculation for distance if I know the height. Okay, because from MGH, okay, and then I can also try to use the trigonometry that I have just now. So our intention now is we want to try to find the gravitational potential energy. Okay, we know exactly that kinetic energy is 0. Okay, final kinetic energy is half mv square. So v is this one. I put back. So this one is u, rest. This one is v. When it is at rest, that means the speed is 0. So mass. And then I have distance travel, that is the one that we want to find. I think we can find h first, right? So because if we are able to find h, we can use the fact that we have the angle 30 degrees here to find the value for h by looking at d. Okay, so since we have final and initial already, we can try to calculate the gain in kinetic energy. So gain in kinetic energy is final minus initial. Since final is this one, initial is 0. So I get 60.025 joule. Okay, so that also gives us the loss in gravitational potential energy to be the same, because as soon as this particle, okay, even though this is box, you can also try to look at it as if it is a particle, roll down, okay, go down the inclined plane here, all the gravitational potential energy is converted into kinetic energy. That's why both of them is the same. So I can do the calculation for MGH. I can find H, and at the end from that H, I can find D. Okay, so I proceed the calculation here. So I do change in GPE, right? So able to give me H to be 1.225 meter. This is the value for my height. Okay, so from trigonometry again, I can use sine, because sine is opposite over hypotenuse. So if I want to find D, I can do D, which is 1.225 divided by sine 30. So which is 2.45 meter it is able to give me the value of this d. Okay, therefore the distance moved along the slope is 2.45 meter. Okay, so now let's look at the second one. The second one here, a rough slope. Okay, inclined at an angle of 30 degrees to the horizontal. The same exact situation, but now the slope is rough. So that means there is no conservation of energy. Energy is not conserved. All right. Instead of it is converted into kinetic and only potential, gravitational potential, it is also converted into friction. So we cannot do the calculation for some sort of things like this because not enough information. Okay. Now we move on to power. I still have time, I think. Okay, power is this is actually the last part, and then we can do a few assessment style question. Power is defined as the rate of doing work with respect to time. Okay, so this is the sort of very definition of power. So if something is doing work, rate means that doing work with respect to time. Okay, so power is calculated by work divided by time. So work is in joule. So joule per second is actually equal to watt. Okay, so the SI unit for power is watt, which is the rate of work of 1 joule per second, right? So usually I advise my student to also sort of memorize this. So joule per second is equal to watt. It allows you to sort of know the unit, final unit without even needing to remember so many things. The watt is a relatively small unit. You will more commonly meet the larger unit. So sometimes we use kilowatt, which is the larger unit for this particular things. Okay, so kilo, you guys know that times 10 to the power of 3. So 1 kilowatt abbreviated to 1 kW, right, which is 1000 watt. Okay, so this one is 1 times 10 to the power of 3 watt. If you recall the prefixes that you learn, so we have pico, nano, micro, millicenti, and so on. So watt is 10 power 3. So that means this is also equal to 1000 joule per second. Okay, joule per second because 1 watt equal to 1 joule per second. Consider a force acting for a small time interval t over a small distance d. Okay, so we have a force, and then we have a time interval t over a small distance d, right? So again, we recall joule per second. We have power, the formula, work divided by time. Okay. So work done equal to F times D. This one we have established before this, right? So power equal to work divided by time, work in joule, and then time in second. All right. So power, we can also get the power in this form because this work here, I sort of need to erase this first. Let me erase. Okay, so this one, so this one is work, work is FD, so here FD over time, right? So we can do that, and then we have F times D over T. So distance divided by time. Okay, if you recall from mechanics, kinematics, the first few chapter, you have distance divided by time is just equal to velocity. So you have another equation to find power. Instead of just by using work divided by time, you can also use power is equal to force times velocity. The power of an engine or machine moving at a speed v subject to a driving force is Fv. Okay. So now let's look at this example. A car exerts a driving force of 1,500 Newton. Okay, this one I can say this is a driving force. Okay, sometimes people put driving force D. Right, traveling at a constant speed. This constant speed is very important. Constant speed indicates it has constant speed. Acceleration to be equal to 0. Oops. Okay, equal to 0. Okay, constant speed. So it didn't accelerate. So of 35 meters per second, calculate the power of the engine. So we need to calculate the power. So I think we have the formula for it. Power is equal to force times velocity. So force is 1,500. Okay, velocity is 35. All right. So we get 52500, 52,500, which is watt. okay, which is this one. And again, we try to put it in kilowatt, so we get 52.5 kilowatt. Any question who need to ask anything, you can just ask. Okay, now we have the third question here. A cyclist is traveling along a horizontal road at a constant speed. What is it? Someone asking?
Ini yang
Hello. Okay. I thought someone is asking me. If you didn't want to ask question, maybe you can switch off your mic. If you do want to ask question, you can proceed asking. Okay, no, Okay, a cyclist is traveling along a horizontal road at a constant speed. Again, constant speed of 7 meters per second. So we sort of has A equal to 0. Okay, acceleration to be equal to 0. If the cyclist experiences a total resistance to motion of 20 Newton. Okay, so this is the total resistance to motion, means that I can say that this is the force due to friction. Find the power produced by the cyclist. So we want to find the power. Okay. Since the speed is constant, there is no acceleration. So just like what I told you just now. So therefore, driving force is equal to force due to the resistance. Okay, remember, from Newton's second law, F equal to ma. Okay. So if I were to sort of draw what actually happened to the cyclist, and I don't want to draw the cyclist because I'm bad at drawing, but you can see that if there is a driving force this side, right? And then if there is a force due to the resistance at this side, right? We can sort of do the calculation where the one at the right hand side, D minus F, this one is from forces and free body diagram, equal to ma. And then since acceleration is just equal to 0 because of constant speed, so this one I can make it equal to 0. That's why I have here driving force is equal to resistance force. Okay, so this allows me to get this calculation. So driving force is 20 Newton, velocity is 7 meters per second. So from the equation of P equal to F times V, okay, so I can try to find the value for the power, which is F is 20, velocity is 7, so 140 watt, which is the power. Okay. Okay, now we move on to the last part. We have a few assessment style question here. Usually I give it to students so that the student can prepare for their exam or test. Let me drink water for a bit. Okay, so let's say we have a car of certain mass of 1000 kg. Move along a straight horizontal road. Again, horizontal is along x-axis, right? The car engine is working at a constant rate of 45 kilowatt. Okay, so looking at this, I know that I can also put here. So this is mass. Okay, watt is the unit for power, and we have total resistance of motion. This one resistance, not driving force, but small f. Usually I sort of use small f for resistance because I want to differentiate between driving force and resistance. Find the acceleration of the car when its speed is 15 meters per second. Okay, so when we have the car with the speed of 15 meters per second, so I can say this is velocity, right? We want to find acceleration. Okay, I know that probably for this kind of question, I need to sort of use a bit of the one that is from force and free body diagram. The car comes to a hill which is inclined. Okay, this is important. They give you the extra condition. We have an angle of alpha to the horizontal. Okay, so if I were to draw this kind of situation, I have something like this. And this alpha here. Okay. But you are also given with sine alpha equal to 0.1, all right? So instead of putting that opposite hypotenuse or something else, you can have the value for sine alpha already. So you don't need to know the degree or the angle here because you have that sine alpha equal to 0.1. This will help you a lot. The resistance to the motion of the car is unchanged, okay? This is another thing. resistance to the motion of the car is unchanged. So you need to know that this 500 Newton frictional total resistance force is not changing. It is just the same. Okay, so we do A first. Okay, question A, we have power. When I do the physics question, I will try to list down all the parameter, right? So you see the first one is power 45,000 watt, velocity 15 meter per second, mass 1000 kg. This small f indicates that it is a force due to the resistance, 500 Newton, force due to friction, and then sine alpha is 0.1. Again, this is the condition from the incline. To calculate the acceleration, it is necessary to calculate the driving force. Actually, the sine alpha we can use for second question, because the first question we don't involve any kind of angle. Okay, again, this one we need to use a bit of Newton second law, F equal to ma. All right. So calculate the driving force. I have power equal to force times velocity. Okay. So if we want to find this driving force, I can try to find this sort of equation that I can use. Okay, power equal to force times velocity. So I can rearrange this equation and get force equal to power over velocity. So since power is there and then velocity is there, I am able to find this force. All right. So why is that important that we find this driving force? Because from F equal to ma, okay, we know exactly what happened. D going to the right, 500 Newton going to the left. So that means D minus 500 equal to ma. Okay. Since mass is already given, right? So mass is given, we know it already, which is 1000. Acceleration is the one that we want to find from the question. But the driving force is not also there. But since we have this particular equation that will allow us to find the driving force by looking at the power and velocity. So we can do force equal to power divided by velocity, so that we can use this force so that we can substitute it into this D, right? So I do this here. So I have my D, which is D indicates driving force, driving force. So 45,000 divided by 15, which is the velocity, 3,000 Newton, the driving force. So applying Newton's second law, F equal to ma. Again, in this condition, acceleration is there. Before this, we have constant speed, but here we have acceleration, right? So you can also see it from this sort of diagram here where we have A to this side. Okay, F equal to ma. So I have since the driving force is 3,000 minus 500. Okay, 500 is a force due to the resistance. Mass is 1000. So I am able to find my A. So at the end, I have A to be 2.5. Okay. So again, the unit for acceleration is 2.5 meter per second Okay. Therefore, the acceleration of the car, it is traveling at 15 meter per second, is 2.5 meter per second That's the answer for the first one. Okay, actually that sine alpha is for the second question. I look back at the B, so that we want to know the question. Let me erase the one that is unlikely first. Okay, again. So for the second question, we want to try to find the maximum speed of the car up the hill. Okay, actually this condition here is given for the second question. If sine alpha is 0.1, okay, so you are given with up the hill when it is working at the rate. So you also has the same power. Power is also the same, right? So I try to list down all the condition that I have here, right? So before calculating, we know something like this. Right, so for this question, you need to be able to also understand something related to forces and free body diagram, where we have a force in 2 dimensions, right? So again, we have the power. We sort of have the same kind of situation where power is 45,000 K. 45 kilowatt. Okay, I sort of use the same condition where I have a 500 Newton here, and then this driving force going up. Okay, so from forces and free body diagram, if I were to have this inclined plane, right, I need to make sure that all the forces is parallel to this coordinate system. Let's say I want to have a coordinate system like this. So this is the y, this is my x. Okay. So I try to look at every single force that I have on this inclined plane. Okay, I try to look at every single force. I want to make sure that this is the condition when we want to do the calculation for forces, free body diagram. Okay, I want to make sure that every single force that we have, 500 Newton is force due to the friction, and then driving force going up. All the forces needs to be parallel to my either y or x axis. Okay, you can see R is parallel to y. We don't have a problem with R. Driving force is parallel to x, so we don't have a problem with driving force. Also 500 Newton here is also, which is the force due to friction, is also parallel to x. Okay, so but the one that we have a problem with is this one, mass times gravity. Okay, the force due to the gravity. Sometimes we even because mass is already 1000, so mg lah. Okay, now what do we need to do is, because we have a problem with this mg, we need to break it up into its x and y component. Okay, so I know that this one, I can break it up. I have mg y, because it is vertical, and then I have mgx. Right. Okay, let me just erase the mg so that you guys can see the difference. Okay, so I have mgy going down, mgx going to the left. Now that I have something like this, I can do the calculation. Why is that? Because all of my forces is already in parallel to my coordinate system. Okay, this coordinate system I make it like this because it will give me the idea on how to do the maths for this kind of question. All right, so now let's try to I change the color of the pen. Okay, we want to try to look at x component. X component means that, okay, the one that is parallel to our x-axis. Okay, so we have D, driving force, going up. We have 500 Newton going to the left. And then we have mgx going to the left. Okay, one more thing that we need to do is we need to also resolve this angle theta. Okay, so if we want to resolve this angle theta, we want to also know that which one between this, if I try to make it big, this one mgy, this one mgx. Oops. Okay, so I have this mgx, mgx, okay, mgy. Actually, the angle theta at this incline is just equal to this angle theta. Okay, so that means from trigonometry, so if we want to find mgy, right, so we can use cos theta, but if we want to find mgx, we can use sin theta. Okay, here is alpha. So since sin alpha is already given, sin alpha is already equal to 0.1 from the question. So given to me this kind of condition, so I can just use that lah. So I don't need to do some sort of difficult calculation to do the maths for getting the to resolve the x component of this mass due to the gravity. Okay, so that one is sin alpha. So now I can do the maths here where D, I use pointer, D minus 500 Newton minus mgx. Okay, so I have something like this. D minus 500 Newton minus, this one is mg sin alpha because of the angle. This one is sin mgx. And then I have equal to 0. All right. So, and then at the end, what I can do is I can try to do the calculation to find the value for D because we want to calculate D in the first place. Okay, again, the acceleration is equal to 0. Why is that the case? Again, from F equal to ma. F equal to ma. Because the stated in the question in the beginning, the force, the speed is constant, so that indicates the acceleration is 0. So that's why all of these total forces, D minus 500, D is to the right, that's why minus 500 because my 500 is at the left, right? And then this mgx is also at the left, right? So we have D minus 500 minus M is 1000 G. Sine alpha comes from this mgx, okay? So I get this 1480 to be the driving force for this kind of things, okay? The driving force of the car is 1480 Newton. Okay, so the final question is want to calculate the maximum speed of the car. Calculating the maximum speed of the car, we do using this formula. Again, the same formula. Since the power is given 45 kilowatt, and then the driving force is 1480. So 45,000 divided by 1480, I get 30.4. Which is the velocity, okay, in meter per second. So the maximum speed is this. Okay, I think we have time to do one more. Give me time to drink water. Okay, this is assessment style question 2. We have a stone of mass 0.5 kg. Is sliding down 10 meter, rough plane, okay? Now we need to include the friction at an angle of 50 degree to the horizontal. The stone passes a point A with a speed of 10 meter per second. So this one should be my U, the initial speed. And then 6 meter per second should be my V. Okay, so now I can do the calculation looking at this. First, find the loss of mechanical energy of the stone as it moves from point A to point B. So from A to B, I want to find the loss of mechanical energy. Okay, for this, I can see that for loss of kinetic energy, I can do half mv square minus half mu square, right? And then mgh for the kinetic energy. Sorry, GPE. Okay, I sort of give all the parameter on top here so that you guys can easily do the calculation. Okay, wait. Loss of energy of the stone is equal to loss of kinetic energy plus loss of gravitational potential energy. Loss of kinetic energy, I know how to find it, which is delta KE, kinetic energy final minus kinetic energy initial. So I calculate the initial kinetic energy first, right? So I have 25 joule, right? So because of VI is 10 meter per second, I just substitute lah. Mass is 0.5, so I get 25 joule. So final kinetic energy is half, mass is 0.5 kg. And then V final is 6 meter per second, so I get 9 joule. So to find the loss of energy, mechanical energy, so I can do find the loss of KE first, where I have final minus initial, 9 minus 25, I get negative 16 joule, okay? This one is true because it is negative lah, okay? Loss is negative, And then for me to find the gravitational potential energy, I don't have H, okay? Again, I don't have H, but I have 10 here. This is sort of given in the question. And let me just, yeah, it is given from this D is 10 meter. Okay, so to find loss of gravitational potential energy, and because we know that as soon as it roll down, it will experience loss of kinetic energy. Sorry, gravitational potential energy, because all that GPE is converted into kinetic energy. So I can try to find H first. So by using the trigonometry again, the same trigonometry 15. All right, sine is so opposite over hypotenuse. So opposite is H, hypotenuse is 10, right? So H over 10. So and then I can find H by 10 sine 15 lah, right? So, and then at the end, I do the calculation where loss of gravitational potential energy is mgh, right? So 0.5, 9.8 times this one, okay? So I've got 12.7, which is the joule, which is the loss of GPE. So I can add 16 and 12.7. So I get 28.7, which is the loss of energy of the stone due to this sort of motion, right? Okay, then we do the second one. Okay, again, this one, let me just, we recap first what did the question want. Okay, the B, calculate the coefficient of friction. coefficient of friction, remember from force and free body diagram, we have two, mu s, which is static friction, mu k, we call mu for kinetic friction, coefficient of kinetic. So if something is moving, we have mu k. Something is not moving, we have static mu s. So coefficient of friction between the stone and the plane. Okay, we want to calculate that. Okay, so in order to do the calculation for this one, you need to know one simple and very important formula. F, which is the force due to friction, equal to mu n. Okay, sometimes R lah. N is normal force. Or sometimes R here. R and N is just the same. These two is just the same. Because sometimes people put R as the normal contact force. Okay. Okay, calculate both the normal force and the frictional force. Okay, so if we want to do the calculation for this, we need to know N, right? Normal force and frictional force, because we want to use F equal to mu N, right? So in order for us to do that, we can do this kind of calculation. Okay, so again, I try to do the free body diagram for this one. Again, if I have some sort of coordinate system like this, y going up and then x like this. Okay, I did this on purpose, and why is that? X to the right positive, y on top going up positive. That's why I put the arrow going up for x and y. Okay. So from that, I can see that, okay, so if I were looking at normal force, R, R is normal force, I want to look at this, I can try to use the fact that both of this is equal. Why is that? Because this box is not moving in Y direction. You can imagine, this box is not jumping up and down, it is not moving in Y direction. So from the F equal to MA, let's say I am analyzing the one at along Y direction, Fy equal to MA. So since it is not moving, right, so this one can be equal to 0. So along Y direction, we have normal force, right, N, or I can say R here. I think I use R to avoid confusion. Okay, R, all right, so minus with the component down. But again, going down here, we cannot take this 0.5 G or mg. Why is that? Because it is not parallel to Y. So instead, we need to take mg Y. Okay, again, mgy, since the angle 15 degree here is corresponding to this angle that is in between mgy and mg, so we know that theta is here, okay? So this one gives us mg cos theta, okay? So R minus mgy, okay? Which is going to be equal to 0. That's why we get something like this. We can just equate R equal to mgy. Since mgy is just equal to mg cos 15 degree, so that's why I have this, right? So I am able to find normal force to do the calculation so that I can substitute normal force later, so which is 4.373. Okay, so now I can proceed to the next one. If you are not very familiar with that angle theta, why is that correspond? You can ask me later. Just want this few students to ask. I don't want to tell you all. Okay, loss of energy of the stone found in part A. Again, we need to find the work done against friction equal to the work done against friction. So the work done against friction over a distance of 10 meters is 28.7. This is the work done against friction that we get from part A. Which is along 28.5 joule. Okay, so work done equal to force times distance. So we have, if this is the work done against friction, 28.7. So the distance is that. So we are able to find this is the force due to the friction, right? So it gives us the calculation that, okay, so I can just substitute the force due to friction and N so that I get mu, right? So I get 2.87, which is the force due to friction. So I can substitute into my equation F equal to mu N, right? So here, capital F, but usually I favor to put small f as for due to friction. So I have F equal to mu N. I can just sort of rearrange the equation so that making mu to be the subject. So F over R. So F over R, I have F is 2.87, and then R is 4.73. So I am able to get the value for mu to be 0.61. Okay, this one is the coefficient of friction. Oh, ada yang tanya. Okay, sorry. I'm not very familiar with these themes actually, but three significant figures, Rina. 3SF is three significant. That's the one that I do in the class. Usually in physics, I will try to stick to three significant figures. Wait. Sorry, I'm not very familiar with this Microsoft Teams. But anyway, that is the last slide from me actually. 5:10. Okay, I am on time lah. Okay, so 0.61. Again, mu we don't have any unit because mu is just the coefficient or any constant that is related to something moving on a surface. Okay, so that's all. Thank you for listening. So I give the crowd back to the chairperson. Right, thank you. Bye.
Okay, thank you very much to Dr. Afiq. Okay, very good sharing session. Okay, complete with simulation and advanced tool. Okay, so our student is very lucky today because they can actually observe the teaching using the more modern tool in their lessons. Okay, if we want to maybe we can also apply the simulation later on in our class. Okay, so thanks again to our lecturer, Dr. Afiq. So I would like to ask from our student, so is there any question that you want to ask Dr. Afiq regarding these topics?
You can ask me anything, don't be shy.
Yeah, maybe you can also ask about applied of the works, force, okay, not only into the chapter lah. Okay, so is there any question from our students?
So,
Is there any question?
Doctor, can I ask your question?
can.
Is it possible for potential energy to have a negative value?
Potential energy to have negative value if it is a loss of gravitational potential energy lah. So it is possible. So so the sort of situation like that one, I go back to the slide. Okay, so you can see that if we have a point of reference, let's say I give a point of reference here. I give the slide to make it a bit bigger. Okay, so sometimes we can also have height to be negative if we have a point of reference here. So this H will also be negative because we can also set. Actually, that's why in the simulation I give you the idea of we have that frame of reference. So if we try to pick this one as a 0, right? So the one at the bottom will be negative. So let's say this one is -2. And then we can say that mgh, so it will become negative because mass, which is maybe 10, time gravity 9.81, time -2. So this consider that the height is negative, so we can get the negative value of gravitational potential energy. So it indicates the loss of gravitational potential energy. That's why we have that. If I'm not mistaken, let me just go back to the simulation. So in the simulation, we can also that is one of the skating example for that simulation. I think I did. Give me a few minutes. Okay, so in that online simulation, you can see that, okay, so it took a while. Okay. Okay, so you can see that we can also have this reference height here. So if we put this here 0, right? So if I put this sort of EMA here, okay, trying to skate here. So you can see that I try to put here, the one we measure. Let's just go back. And then we can put the reference height. Okay. I go back to this position. So the height is not appearing. So I can also have the negative value lah. It depends on the reference frame. Let me. Okay, you can see if the height is negative, right? So you can see potential energy also become negative. It is because that in physics, this height or the frame of reference of height equal to 0, it is up to us to set that height lah. Okay, so that's why in if you are dealing with later on with the spring, you can see that for a few we have that negative value for the height. Okay, so is that answering your question?
Yes, Doctor. Thank you.
Right.
Okay, so the negative value and positive value can also represent whether the object is away or toward the reference point. Is it right or not?
Yeah. Can also. True. Can also refer to that.
So
but the
it can also be applied to the horizontal plane lah kan?
Yeah, horizontal plane. Yep, usually lah. If the reference frame, you can see that I put the reference frame here in the center to be equal to 0. So the one at the left become negative lah. So that one we can apply to not H, but the D lah, the distance along horizontal motion. Slightly different situation. Okay. But still can get negative lah. Okay. Any other questions?
Okay, is there any other question from audience, students?
In chat box.
Oh, ada. Okay, sorry. Chat box. Why work is scalar? Why work is scalar quantity? Because it has a positive and negative value also. Force time distance. Sorry, Okay, so one of the question is asking, let me share my slide. Okay. Work is scalar quantity. Force time distance here. So work done, we don't have any sort of direction for it lah. So that's why it is considered as the scalar quantity. Because something that has direction, so we consider it as a vector. Okay. Yep. Actually I didn't I'm not very sure about the question. Can someone who is asking to give me the idea? Give me the explanation a bit, Dr. Suziana.
Okay, work, when we measure work, we get the value sometimes in negative and positive value. So it shown that it has position, consider position, direction. So why we call it work in scalar quantity?
Oh, why is it work is a scalar quantity?
State that the work is a scalar quantity.
Okay, all right. Very good question lah. Usually that something that has direction is that we incorporate direction is vector quantity lah. So even work done here, we can say that do we have negative work? That's my first question. Do we have negative work?
For distance in left direction, we get positive also, or we get
Okay. So for the one that is going to the left, we get negative
Yes,
lah.
yes.
So that one is positive work. Negative going to the left lah. So but work done, because it is just dependent on the what we call the parameter or the magnitude only, not the direction. So that's why we consider it as a scalar quantity lah. Very good question lah from Dr. Suziana. Okay, right. Any question? Any other question? Thank you. From the student or from the lecturer can also.
Okay, any other question from student? Okay, but before that, I just want to remind students to fill their attendance link. Okay, for this program, do not forget to fill the attendance links. Okay, Dr. Afiq, actually I have one question, okay, about the applied of the, maybe related to this topic lah. Okay, so if you are looking about rocket launching, okay, so when the rocket launch to the space, okay, we travel to our atmosphere, okay. So as it travels to our atmosphere, the thruster will release off the one we call that the fuel. Okay. So as it travels upward, the mass of the fuel will decrease. So is actually the force is constant or not?
Sorry, what is it? The mass is decreased?
As the rocket thrust toward upward of the sky, okay, the thruster release some of the fuel because it burns to create thruster force.
Okay, thrust force.
Okay, then the rocket will become, we say, low in weight.
Okay, so the weight is decreasing.
Okay, so can we say that the force is constant or not constant? Because I just want to know because when the rocket travel to the higher altitude, is there any effects on the gravitational force?
Of course lah. Wait, someone is also talking. Okay. Of course lah. It also okay. Your who is talking? You can turn off the mic.
Is there any student who want to ask question?
Because the student is talking, but okay. I can see, I can hear the voice. I don't know where. I think host can mute. The question just now is do the mass decrease or?
Maybe you can just answer about, is there any effect on gravitational force as the rocket incline toward the sky?
Okay, so is gravitational potential energy decreasing? Is that what you mean?
Yes.
Oh, okay, no, gravitational potential energy didn't change on surface of the Earth lah. So the gravitational potential energy will still become the same. It's just that apparent wake will change lah. Apparent wake due to the wake of the rocket itself. So it just sort of the wake that the person and the rocket itself feels will change. Not that the gravity will decrease or increase, because gravity will always equal on the surface of the Earth. The same thing as moon and so on. Okay.
Okay, thank you for the answer.
Okay.
Okay, so if there is no more question, okay, so I will remind once again about, can students please fill their attendance form, okay, and then at the end of this session we will have a photography session. Okay, so I hope student can turn on their camera lah, so we can snap and see your face. Okay. So Dr. Suzaina, can we proceed to photography session?
Yes, we can proceed to photography session.
Okay, so all students please turn on their camera. Okay, we will start our photography session in 1 minute. So you have time to make up or do whatever lah.
So this program UITM do it annually? Buat setiap tahun ke?
No, refer to syllabus.
Okay. Okay. Oh, ada Dr. Norizan. Hai Dr. Norizan.
Assalamualaikum Dr. Afiq.
Dah lama tak jumpa.
Ya, betul. Kahwin pula tak sempat nak pergi ya. Tahniah.
Terima kasih.
Mujur tak ucap, nanti dah anak 5 kan. Sebelum dapat anak lagi ucap. Tahniah.
Student boleh open kamera?
UITM masih face to online ke kelas?
Face to face.
Oh, face to face dah. Okay. Oh, sebab hari ni Jumaat cuti.
Betul.
Okay, siapa akan snap gambar? Puan Rina ke?
Rosmawati.
Okay, okay. Okay, so I think we can start
Thank you.
our
Student can open for.
Okay, so I will count 1, 2, 3 and Cik Rosmawati will snap the picture lah. Okay, maybe we can wait another 30 seconds because there are so many cameras open up right now. Okay, so we will start our photography. Okay, in the count 1, 2, 3 and Cik Rosmawati will snap the picture lah. Okay, so 1, 2, 3, smile. Okay, second picture, maybe you can make some love icon or whatever icon you want to do in front of the camera. Okay, another click. Okay, 1, 2, 3. Okay, so I think that is all for today's program, and I would like to once again thanks to Dr. Afiq Arif bin Aminuddin Jafri, because he is very generous to spare some of his time this evening to teach us physics about works, energy and force. Okay, so maybe we can have the last word from Dr. Afiq Arif bin Aminuddin Jafri before before ending our session.
Okay, so first of all, thank you to TF Dr. Suziana for inviting me to become the speaker for the talk, for this invited talk. it is a very pleasure to talk here to your ITM student. Hopefully, from my sharing, the student will get a lot of what I teach lah. Okay. So also I hope it also benefit the lecturer lah when I do the one-day simulation and so on. Okay. So thank you so much to UiTM and see you around.
Thank you, Dr. Afi.
Alright, thank you everyone.
Thank you, Dr. Afi. It's a very
Thank you,
great pleasure
Doctor.
to have you here.
Okay, bye.
Thank you, Doctor.
Okay, Assalamualaikum.
Waalaikumsalam.
Okay, thank you for all students and for all the lecturers who are involved in this program. Okay, so now we can close our program. Okay, thank you very much and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi